We may also be given a locus of points which involve the argument of a complex number. If you don't remember what the argument is, please watch my previous video on it, but the argument is the angle a complex number forms with the positive real axis. So say this is some complex number z, this angle it makes with the positive real axis tells us the argument of the complex number, which we write as arg z. So given some complex number z1, the locus of points that satisfy z minus z1 is theta. This describes a half line from this point z1, which makes an angle theta with a line that's parallel to the positive real axis. Let me explain what I mean by that. So let's draw z1. Say this is a point z1, and z is just any complex number. It represents a general point. So any point such that the argument of z minus z1 is theta. So looks something like this. So z can be any point that lies on this line as long as this angle or this argument is theta. The line that it makes the argument with is parallel to the real axis, and this describes any point that lies on this line. So z could be any of these points, and this line from extending up from z1 at an angle of theta to a line parallel to the real axis, this is known as a half line. A half line is a line that extends from a point in one direction indefinitely. So it's a line that goes from one point in a certain direction forever, but not in the other direction. So let's look at an example of plotting such a locus. So say we are given that the argument of z plus 3 plus 2i is 3 pi by 4. I'm going to write down the general form. So let's first work out what our z1 is. So I'm going to rewrite this. We can see our complex number z1 must be minus 3 minus 2i, because if we simplify this, we just get this. This is in this form. So let's plot z1 minus 3 minus 2i on the diagram. So I've got negative 3 units along the real axis and minus 2i units on the imaginary axis, so my complex number is here. And we want the locus of points such that the argument of z minus this point is the angle 3 pi over 4. So 3 pi over 4 is, so 3 pi over 4, which is an angle in radians, that is 135 degrees, because pi radians is 180 degrees. So we are drawing an angle to the line that is parallel to the real axis. So this is a line that's passing through the point and parallel, by through the point I mean through the complex number minus 3 minus 2i. It passes through that point and it's parallel to the real axis, and we want the angle that's formed with that line to be equal to 135 degrees. So starting at this point, we're going to form an angle of 135 degrees, so something like this. This angle is 135 degrees, or 3 pi by 4. And this line extends in this direction forever, not in the opposite direction, doesn't go in that direction. It just goes from that point at an angle of 135 degrees to the line parallel to the real axis. It goes on indefinitely forever, so any point that lies on this line is described by this locus. Now let's look at regions on the Argand diagram. Let's say we have this expression, which we know describes the locus of points that lie on a circle, because it looks like this form, where r is the radius. Instead of an equality symbol, when we have a less than or equal to or any of these symbols in between, This now describes a region of points on the diagram. So let's plot this region. We know it looks like a circle. Let's find the center. So I'm rewriting this in our desired form, and we have this. So the center of the circle is at coordinates 4, 2. So here is the center of the circle, and the radius is 2. So this is a circle with a radius 2. And since we're looking for all the points that have a distance, remember this represents a distance, looking for all the points that have a distance of less than or equal to 2 from this center. So what that means is all of the points lying inside the circle will satisfy that inequality, because all of those points either have a distance of 2 from the center or they have a distance less than 2 if you pick any point inside that circle. So that is the region described by this expression.